So at a very high level, what does math have to do with machine learning? Like, why math for machine learning among all the things that we could be talking about? And all programming involves mathematics at some level. Mathematics and programming and computers have been tied together since the inception of computer science and programming. Machine learning in particular, though, is programming by optimization. The way that we program computers to do things in machine learning is through optimization. And in order to understand optimization, in order to understand what it is that we're optimizing and why and how that works, we need mathematics. And this is what makes machine learning such a more mathematical discipline of programming than something like web development or database management or any of the other different branches of programming that are popular these days. And so in this series, we're going to cover several of the ways that optimization and machine learning intersect or interact. Linear algebra, which will help us understand the objects being optimized. Calculus, which will help us understand how it is that we optimize those things. And then probability and statistics, which will help us understand what that thing is that we are optimizing, that we are making better. So we'll start with that section on linear algebra, which is to understand the objects that are being optimized. So the takeaways for today are that linear algebra is important and why it's so important. That linear algebra, despite its name, is actually not that much like algebra. And that the SVD, or singular value decomposition, is a matrix version of refactoring, a common technique in programming. First, linear algebra is important. Why do we care about linear algebra? First pass definition is that linear algebra is the mathematics of arrays. An array is a collection of numbers, a sort of block-like collection of numbers. Those numbers are usually we think of them as being floating point numbers in a computer or real numbers in mathematics. And lots of objects are represented by arrays in machine learning. Our data is going to be in an array. There will be our inputs and our outputs. If our inputs are images, there are going to be arrays of numbers that represent that image. Very often, our models, which are like the equivalents of our programs in machine learning, will be represented by arrays or by collections of arrays. And then the internal computations even of those models will be represented by arrays as well. And so the core operation in linear algebra, the core operation that we use to manipulate those arrays is matrix multiplication. So a couple of examples of matrix multiplication in action. You may have heard of the dot, scalar, or inner product, the correlation or the covariance in statistics, linear and logistic regression, ideas from classical machine learning, principal components analysis, also a bunch of useful algorithms outside of what you would think of as machine learning, discrete Fourier transform, PageRank, then things in machine learning, again, hidden layers of neural networks, convolutions, the second order methods for optimization, in LBFDS. Matrix multiplication is essentially the operation at the core of every single one of these examples. And in the end, GPUs, you may have heard of the importance of GPUs, graphics processing units. GPUs are a huge part of what drove this huge explosion in machine learning recently. And they were originally designed for video games, and they made video games faster and better. But they ended up also making machine learning faster and better because underneath it all, both graphics rendering and machine learning require linear algebra. And that matrix multiplication is surprisingly simple, despite how many things it can be used for. So we have our arrays of numbers. So we have one array here on the left, another on the right. That's on the left side of the equal sign here. And that's going to result in the output of another array. So if I take two matrices and multiply them, I take the rows of the first matrix and the columns of the second matrix, and I combine those together to get the elements of the output. And what I do is I take each number in this row and each number in this column, and I multiply them together. That gives me a whole bunch of numbers, and then I add them up, and that gives me this final number here. I reduce them down with this sum operation. So mathematically, that might be written that if I were to matrix multiply x and y together here and look at the ith row and the jth column, then what I'm going to do is take the ith row of x, the jth column of y, and multiply their entries and sum it up. And if I want to get all the entries of that output of that matrix multiplication of x and y, I just do that for every row and for every column. Matrix multiplication takes two matrices where one has the same number of rows as the other has columns and turns them into a single output with the same number of rows as as the first one and the same number of columns as the second one. It's relatively simple given how many things it's capable of doing, but it's also kind of a weird and specific rule that if I just told you, oh, here's how we're going to combine collections of numbers, there's no obvious reason why you would do it that way. And from here, I think a lot of linear algebra tutorials would just jump straight into algebra. They would give algebraic definitions in terms of equations of a whole bunch of key concepts and then start manipulating those equations, manipulating matrices. And I think this is not the right tack to take here because I think it doesn't give you a motivation for why we're doing that rule and how you should really think about linear algebra rather than thinking of it as manipulating a bunch of equations. Let's dive into this first of our major concepts, that linear algebra is not like algebra. Linear algebra is really often taught like algebra, first discovered in this world where people were really concerned with solving equations. And linear algebra kind of looks like algebra because it's got addition and it's got multiplication and there's rules for combining them. So that looks a lot like algebra. And lots of linear algebra classes spend their time on just those computations, manipulations, determinants, eigenvalues, things like that. And folks end up getting pretty confused because the rules are complicated and reasoning with equations is pretty hard and unintuitive. It took me a very long time before I became comfortable just doing that kind of algebraic manipulation with linear algebra. But that's not the only way to understand linear algebra. There's lots of other ways to look at it that are more fruitful. And so one of them is a sort of geometric view of linear algebra that I think is best put forward by this YouTube series by the YouTuber 3Blue1Brown, formerly of Khan Academy, The Essence of Linear Algebra. And that views linear algebra as the study of linear transformations of spaces, of transformations, of rotations, reflections, and scalings of a grid. And so that's one interesting way of looking at it. And I recommend you check out that YouTube series. It's very beloved. There's also other mathematical ways of understanding linear algebra that don't have to do with equational reasoning. For example, graphical linear algebra approach, which came out of the world of category theory in the last 10 years. This nice blog post series by Pavel Sobocinski that basically views linear algebra as what happens when adding meets copying, which is an interesting alternative way of looking at linear algebra and uses diagrammatic reasoning like you see on the bottom right of the slide rather than equational reasoning. It's completely rigorous. It's in some ways even more rigorous than the normal way that you do linear algebra, but it involves this very spatial picture-based reasoning. So if you're interested in abstract math, that's a fun direction to go. But I don't think either of those necessarily is the right approach for folks who work with software and hardware. For them, I think the right way to think about linear algebra is that linear algebra is more like programming. So matrices are our functions, shapes are the types of our data and our functions, and multiplication is function composition. And this approach uses a bunch of ideas from programming, from computer science, rather than from, say, physics or from abstract math. So in programming, we combine functions with matching types through function composition. So we combine the functions together that way. In linear algebra, we combine matrices that have matching shapes through matrix multiplication. When we're doing programming, we define one function in terms of the others. So if I wanted to make a function that checks whether a string is too long to tweet, maybe tells a user, hey, this is too long, shorten that string up if you want to be able to tweet it. I might define that by composing a couple of functions. First, I check the length of the string, then I check whether the length of that string is over 140. So I combine these two functions together, that gives me too long to tweet as a function. That composition, if I were to look at the type of len, it takes, say, a string and returns an integer that's the length of the string. Over 140 takes an integer and returns a Boolean, a true or a false value. And so too long to tweet, take those two pieces, those arrows, and slap them onto each other. It now takes a string and returns a bool. That composition of those two functions takes the input of one to the output of the other in terms of types. And we can see that if we draw the typical way of representing functions in at least the American mathematical education system, when you first learn about functions when you're in school, you see a picture that looks something like this. All the inputs are in a little circle on one side, then the function is like an arrow that points from one of those inputs to the output. So A and B are both strings of length 1. The beginning of the declaration of independence when in the course of human events it becomes necessary. That's a strength of length 8007. 8007 is bigger than 140, and so the Declaration of Independence is too long to tweet. So you can read off how these functions behave by following those arrows. So we get this purple arrow representing too long to tweet by following these red and blue arrows representing len and over 140. And really, this is the essence of programming. If you ever do functional programming, especially pure functional programming, this is all that you do, and it's enough to do anything that you can do in any language. We often do slightly different things in other programming languages, but in principle, this is the core of what we are doing when we are programming computers, combining these things together. And in linear algebra, we do much the same thing. So when we want to do function application, when we want to apply a function to data, that's matrix vector multiplication. Often we might think of matrix vector multiplication as an equational thing, as just, oh, matrix vector on the left-hand side is equal to the thing on the right-hand side, the way you would say 2 + 2 = 4. But the view that I'm I'm trying to put forward here is that you should instead think of this as M of V. M, the matrix applied as a function to the vector V, is equal to the thing on the right-hand side, which for now we're just calling MV. Under that view, a matrix is a function that takes in arrays with a certain number of rows and puts out arrays with a certain number of rows. In this case, the number of rows in that vector, the sort of length of that vector is just k here to emphasize it could be a bunch of different things. But the output, the number of rows in the output, is given by the number of rows in that matrix. It's, in this case, 3. So like that function too long to tweet had a type signature that said it takes in strings and returns bools, this matrix has a type signature. It takes in arrays of length k1 and returns arrays of length 3, 1. Let's just pick a particular in arrays of length k1 and returns arrays of length 3, 1. So let's just pick a particular matrix here, this matrix X here that's 1, 0, 0, 0, 1, 0, and let's view it the way we would view a function in that ovals and arrows way of viewing things. You can see the inputs on the left, the outputs on the right. So the outputs 0, 1, 2 and 0, 1, 5 both get taken to the same thing. And just as an exercise, if you were to name this the way you name a function in programming, what name would you give this matrix X here? When we're doing math, we often think of these things as variables. We don't give them descriptive names. We give them names like X and W. But when we're thinking about functions, we often give them a specific name. So this X here is taking in inputs that look like things on the left and returning things that come out on the right here. When we combine matrices through matrix multiplication, when I take two matrices and multiply them together, that is like function composition. That is like that combination of two functions. So for example, we could take that matrix X and then apply on the left matrix Y, and we would then get a different function, a different matrix that does something different to its inputs. As an example here, I've got this first matrix we already talked about strips off that last entry. So it strips off the Z-axis here. So then we get a vector that looks like this one in the middle here. So that red arrow here points from the inputs on the left to the outputs on the right. And then we can chain that with that second matrix, this matrix indicated in blue here, the Y matrix that takes two-dimensional inputs and returns two-dimensional outputs. And that one zeroes out the Y-axis. So then we end up with a vector that lies just along the X-axis with only the first entry of that vector that went in. And so this is, I think this way of drawing things is maybe a little bit more common for vectors than that oval way of drawing things. So I wanted to make sure we covered that. The combination of those two things, the combination of those two functions is itself also a function, and it's also, in fact, a matrix. And that matrix is obtained from the two submatrices by doing matrix multiplication. So that matrix multiplication rule. Why did we use that specific matrix multiplication rule? It was so that this would be true. It was so that if we did matrix multiplication on the left of this matrix by this matrix, we would get this matrix representing their composition. So that is the reason for that matrix multiplication rule, fundamentally. This is the approach for thinking about linear algebra that I think is most fruitful for doing machine learning, and I think also for a lot of other branches that linear algebra gets applied in. But the remaining question is why linear algebra for machine learning? We've understood a little bit more about linear algebra, but we haven't really tackled why this is important for machine learning yet. I said that we use arrays to represent functions and represent data in machine learning, but why this? And what kinds of functions can we represent that way? So why basically is linear algebra so important for optimization and hence machine learning? I think the right tack to get to understanding this is to think about how would we represent functions as data. So the fundamental question, if we want to program by optimization, is that we need to be able to represent programs and manipulate them. So we're going to start with a program that doesn't work and then slowly over time obtain a program that does work. That's that process of optimization. In order to do that, we need to have that program and we need to be able to manipulate it somehow. The normal way that we represent programs as data is as strings, right? The usual way is buildwebsite.py, right? That is actually in the end a string of characters, and that's how humans tend to manipulate programs. In general, we could also represent our programs as dictionaries, as lookup tables. It's basically applying that oval and arrow view of functions to your program. So those are different ways to do it. Neither one is actually really good for optimization. If we want to optimize things quantitatively, actually the way that we represent programs is horrible, right? That's an absolutely horrible way to represent functions if we want to be able to optimize them. So just take an example. Very simple Python program to check if a number is odd and return whether it's odd or even as a string. Pretty much any single character change to the code on the left would break it, would make it not do the right thing, or it would completely break the program, make it not valid Python anymore. It's a great way for representing programs in order to get programmers to work with it, for humans to adjust the behavior of programs. But for a computer, that's really difficult to be able to make these coordinated changes. And it's very difficult to make that numerical, quantitative in a way that we can actually automate this process, which is the goal of machine learning. So the main way that we make progress is by restricting ourselves to a smaller set of functions and focusing on making those work well. And so looking for a more limited data type that maybe doesn't necessarily represent all possible functions, but is still powerful. If we focus on easy to optimize functions, we'll get two separate branches of machine learning, one based off of trees that gets you to things like random forests, gradient boosted trees, things like that, which we won't be talking about. And the other direction, which is towards using arrays. So using matrix multiplication as function application and thinking about only linear functions, at least at first. And the benefit is that arrays are really easy to change just a tiny bit. If I make a tiny change to the entries of a matrix, then I'll get a small change in the function that the matrix applies. So the outputs will only change a little bit if I change the matrix a little bit. And as we'll see when we talk about calculus, that's huge. That's extremely valuable. And then, of course, there's what we talked about, linear algebra being able to be made fast and there being all these really useful things that you can do with it. And so at its core, this is why linear algebra is so important for machine learning. I want to go over a little bit what I mean by arrays represent linear functions. And now it's finally time to do a little bit of algebra. There's basically two rules for something to be a linear function. It needs to respect the first rule here, f of a plus b is f of a plus f of b, distribution over addition rule. And then it also needs to respect this distribution over multiplication rule, f of lambda times a is equal to lambda times f of a. So that says if I scale the input, then I just scale the output. And if I look at the output on the sum of two inputs, it's the sum of those outputs. So what this allows us to do is rearrange a problem that may come in looking like f of a plus f of b, which would require us to compute something twice, and swap that around just computing it once, f of a plus b. The reason why we have those two rules is because that means that linear functions play really nicely with weighted sums. If I combine those two rules, I can use them over and over again. If I multiply by a bunch of different scalars, and if I add a whole bunch of things together, that's what this thing is doing here in the center, I can pull that out as well. Just as I could pull the plus sign out from the inside of the function application here, and I could pull the scalar multiplication out to the outside of function application, I can do that with a whole bunch of sums and multiplications. So anytime that I do a weighted sum of things, my linear function will be able to either go on the inside or the outside. And that's huge. Weighted sums show up all over the place and basically makes linear functions really easy to reason about. So we'll see how this works with how linear functions interact with the number 0. So first off, 0 is going to always be sent to 0. So we get this from our multiplication rule. If I apply f to 0, that's the same as applying f to lambda times 0, because lambda times 0 is 0. And I can then pull that out, which means that lambda times f of 0 is equal to f of 0. That can only be true if f of 0 is 0. If inputs collide, we can also determine, using these rules, that more things have to be sent to 0. So if two things get sent to the same thing, then their difference has to be sent to 0. If f of a minus f of b is 0, so if a and b are sent to the same output by f, then f of a minus b is 0. So that difference between a and b, that thing gets sent to 0. So we can do that. We're just pulling that minus sign inside. And if you're being really technical, we're basically pulling the minus 1 inside and then using the addition rule. Anything that is sent to 0 is called the kernel of that function. A minus b here is in the kernel of the function. So one thing that comes out of this is you can also check that result that we got, that 0 has to be sent to 0, because if I set a and b equal to each other, then I get that same result. So 0 is in the kernel. 0 is always sent to 0. Other things might also be in the kernel. That kernel there is made up of weighted sums. Going back to this idea of weighted sums, if f of a is 0 and f of b is 0, then a plus b is also sent to 0. So f of a plus b, that's the same as f of a plus f of b. Those are both 0, so the output is 0. And so this collection of things that get sent to 0 is made up of weighted sums. If I take a whole bunch of things that are all sent to 0, and all I can do is combine them by weighted summing, then I'm still going to stay in this collection of things sent to 0. The same is true of the collection of things not sent to 0. Anything not in the kernel, if I combine those things rules, is because that means that linear functions play really nicely with weighted sums.
I'm visualizing it. I fucking see it right now. I see a lot of SVD going down in here, boy. A lot of SVD, a lot of shenanigans going down. I'm visualizing it. I fucking see it right now. I see a lot of SVD.
Assume we have a 2 cross 2 matrix A and a unit vector V1, which is shown using this dark blue vector. We know that if we multiply this vector V1 with matrix A and call it Y1, then A will transform V1 into a new vector, Y1, by either stretching it, squashing it, rotating it, or flipping it, depending on the entries of A. Look at this red vector, which is the transform vector y1. Now, if we slowly rotate this vector v1, then every time it turns to a new direction, A will again transform it into a new output vector, or a new y1. As v1 goes around in a circle, the transformed vector y1 also moves around, but in its own unique pattern. Now suppose we're asked to find an orthogonal set of vectors, or in simple words, a set of vectors that are perpendicular to each other, that when transformed by A will remain orthogonal. One way we can do this is by considering another vector, v2, which I will show using this blue color, such that it will be orthogonal or perpendicular to v1. Once we have these two perpendicular vectors, we can transform both of them using A, and then check whether the transformed versions y1 and y2, which we will show using this maroon-colored vector, still remain perpendicular. See when I rotate v1 and v2 together. The angle between y1 and y2 also changes. For the time being, let me hide v1 and v2 and only show the transformed vectors. We can clearly see that at this orientation, the angles between y1 and y2 is around 90 degrees, which means for this value of v1 and v2, both the transformed vectors, or these, are orthogonal. Similarly, at this orientation, the angles between y1 and y2 is again around 90 degrees, which means for these different sets of v1 and v2, both the transformed vectors, or these, are orthogonal. Keep them aside for a while. Now let us do some algebra and see some magic. We have these two equations with us, right? v1 and v2 are already unit vectors, but y1 and y2 are not. So we can represent it using some scalar value sigma, which acts as the magnitude, and the unit vector u, which
Professor Dave explains. Previously, we saw how the eigenvalues and eigenvectors of a matrix can be used to diagonalize
So what concept or theorem in linear algebra or in math you find most beautiful, that gives you pause, that leaves you in awe?
Well, I'll stick with linear algebra here. I hope the viewer knows that really mathematics is an amazing, amazing subject, and deep connections between ideas that didn't look connected. They turned out they were. But if we stick with linear algebra, so we have a matrix. That's like the basic thing, a rectangle of numbers. And it might be a rectangle of data. You're probably going to ask me later about data science, where often data comes in a matrix. You have, maybe every column corresponds to a drug, and every row corresponds to a patient. And if the patient reacted favorably to the drug, then you put some positive number in there. Anyway, rectangle of numbers, a matrix is basic. So the big problem is to understand all those numbers. You got a big set of numbers, and what are the patterns? What's going on? And so one of the ways to break down that matrix into simple pieces uses something called singular values, and that's come on as fundamental certainly in my lifetime. Eigenvalues, if you have viewers who've done engineering, math, or basic linear algebra, eigenvalues were in there. But those are restricted to square matrices, and data comes in rectangular matrices. So you got to take that. You got to take that next step. I'm always pushing math faculty, get on, do it. Singular values. So those are a way to find the important pieces of the matrix, which add up to the whole matrix. So you're breaking a matrix into simple pieces, and the first piece is the most important part of the data. The second piece is the second most important part, and then often, so a data scientist will, like, if a data scientist can find those first and second pieces, stop there. The rest of the data is probably round off, experimental error maybe. So you're looking for the important part. Yeah.
So what do you find beautiful about singular values?
Well, I didn't give the theorem. So here's the idea of singular values. Every matrix, rectangular, square, whatever, can be written as a product of three very simple special matrices. So that's the theorem. Every matrix can be written as a rotation times a stretch, which is just a matrix, a diagonal matrix, otherwise all zeros except on the one diagonal. And then the third factor is another rotation. So rotation, stretch, rotation is the breakup of any matrix.
The structure of that, the ability that you can do that, what do you find appealing? What do you find beautiful about it?
Well, geometrically, as I freely admit, the action of a matrix is not so easy to visualize. But everybody can visualize a rotation. Take two-dimensional space and just turn it around the center. Take three-dimensional space. So a pilot has to know about, well, what are the three? The yaw is one of them. I've forgotten all the three turns that a pilot makes. Up to 10 dimensions, you've got 10 ways to turn. But you can visualize a rotation. Take the space and turn it. And you can visualize a stretch. So to break a matrix with all those numbers in it into something you can visualize, rotate, stretch, rotate, is pretty neat.
Yeah,
pretty neat.
That's pretty powerful.
The singular value decomposition.
If I combine those two rules, I can use them over and over again. If I multiply by a bunch of different scalars, and if I add a whole bunch of things together, that's what this thing is doing here in the center. I can pull that out as well, just as I could pull the plus sign out from the inside of the function application here, and I could pull the scalar multiplication out to the outside of function application. I can do that with a whole bunch of sums and multiplications. So anytime that I do a weighted sum of things, my linear function will be able to either go on the inside or the outside. And that's huge. Weighted sums show up all over the place and basically makes linear functions really easy to reason about. So we'll see how this works with how linear functions interact with the number 0. So first off, 0 is going to always be sent to 0. So we get this from our multiplication rule. If I apply f to 0, that's the same as applying f to lambda times 0, because lambda times 0 is 0. And I can then pull that out, which means that lambda times f of 0 is equal to f of 0. That can only be true if f of 0 is 0. If inputs collide, we can also determine using these rules that more things have to be sent to 0. So if 2 things get sent to the same thing, then their difference has to be sent to 0. If f of a minus f of b is 0, so if a and b are sent to the same output by f, then f of a minus b is 0. So that difference between a and b, that thing gets sent to 0. So we can do that. We're just pulling that minus sign inside. And if you're being really technical, we're basically pulling a -1 inside and then using the addition rule. Anything that is sent to 0 is called the kernel of that function. A minus b here is in the kernel of the function. So one thing that comes out of this is you can also check that